In this video, I want to talk about volume, which is, of course, the property of how much space a three-dimensional object occupies. And that's kind of key. A lot of people think it's how much some sort of container holds. But you want to say something like a textbook has volume, right? And so it holds nothing because there's no place for it to hold. So the best idea to talk about volume is to think of it as the amount of space that a three-dimensional object occupies. And just like all the other measurements before, the best we can do is compare it to something. And the things we compare it to are usually cubes. We're in 3 dimensions, so the object we need to compare something to is a 3-dimensional object. So we use these little 1 unit by 1 unit by 1 unit cubes. And so it's 1 unit cubed. It's a 3-dimensional measurement, so the units are cubed. 1 unit for each of the 3 dimensions. And of course, you're asking, well, how many of these little cubes take up the exact same space as the object that you're measuring? And that number of cubes, well, that's the volume in the unit that you're picking. Okay, let's do a little warm-up exercise, a little dimensional analysis. So we know that 1 inch is 2.54 centimeters. And an interesting fact, this isn't a rough conversion. They've decided that this is literally the definition of an inch. It's 2.54 centimeters. So my question to you is, well, what is 1 inch cubed in centimeters cubed? How many centimeters cubed fit in 1 inch cubed? So think about dimensional analysis here and see if you can do this. Pause the video now and try it yourself. Okay, now that we're back, so we have 1 inch cubed. So remember, this is like 1 inch by inch by inch. So there's 3 inches we're thinking about, 1 for each dimension. So we need to convert each of the dimensions to centimeters cubed. So we want to, in fact, maybe I'll make this a multiplication, of course. So let's multiply this by the correct unit fraction. I want to get rid of inches, so we'll put inches down the bottom. And centimeters up top. There's one of the inches one of the dimensions converted from inches to centimeters. Let's do it again for a second one. And for the third dimension, here we go. And remember, just as a reminder, each of these dimensions needs to be converted because there are 3 dimensions in a 3-dimensional space. Of course there is, that's why it's called 3-dimensional space. And we're converting each of them from inches to centimeters. Okay, so let's check that our units work out. Well, here's 1 inch, 2 inch, 3 inches cancel with these 3 inches, inch by inch by inch. And we're left with centimeter by centimeter by centimeter. So our unit looks good. It's centimeter cubed. So we just need to figure out what 2.54 times 2.54 times 2.54 is. And I'll just write an approximation here, but you could check. It's really close to 16.39 centimeters cubed. So roughly 16.39 little centimeter by centimeter by centimeter cubes fit inside 1 inch cube. Okay, let's move on now. So just a little quick note here. Sometimes people talk about volume in other units. So they won't say things like centimeters cubed or inches cubed or meters cubed or whatever. They won't talk about lengths cubed. They'll talk about some other things like teaspoons or tablespoons or cups or even liters. These guys are imperial measurements, but liter is a standard metric measurement, but it's not expressed as some distance cubed. But that's okay. I'll tell you the conversion if we ever need to do that. But just note that sometimes you will see non-cubic measurements here. Okay, so now that we know what volume is, we want to be able to determine the volume of shapes. And the shapes we're going to talk about are basically prisms and pyramids. So we're going to start out with kind of the easiest thing, which is a rectangular prism. And then using the ideas of the volume of a rectangular prism, we're going to find the volume of any old prism that you like. And this is by something called Cavalieri's principle, which I'll talk about in a couple of slides. And then once we know the volume of any prism, well, we can go back and we can look at how we can use rectangular prisms to give us the volume of a square pyramid. And then from a square pyramid, we're going to use Cavalieri's principle again and find the volume of any old pyramid that we like. And just for this chapter, when I say pyramid, I do mean a right regular pyramid. So regular means that the base is going to be some regular polygon. So a polygon with equal length sides and congruent angles, so congruent sides and congruent angles. And right means that if you draw a line from the point of your pyramid to the center of your polygon, you get a right angle with the polygon on the ground. So they're the type of pyramids we're going to deal with. And you could think, well, what about figuring out the volume of other shapes? So anything else well, what we can do is we can kind of do what Archimedes did and just measure it by displacement of water. So you can get a little graduated cylinder here and fill it up to a certain amount with water. So I'm going to do that here. Let me change my pen. This one will do. There we go. So let's say it goes up to there with water with nothing in it. Well, let me mark that spot, in fact. So let's say I mark it here. Then I drop in the object. So let me just draw a little object that I drop in. And it's not going to be a pyramid or a prism. It's just going to be some lumpy, bumpy object. And if you think about it, as that lumpy, bumpy object enters the water there, it's going to displace the water up into the cylinder. So it's going to raise the water level. So let's say it raises the water level to there. So let me actually kind of draw this. So there's the water level first. And then it gets raised when I add that that object to something like that. Ooh, that's not what I want. There we go. So it gets raised to something like that. And then, if you can figure out the volume of this water, what's in between, so the volume of that water is the volume of your object. So that's really cool. And it's literally what Archimedes did when he sat in that bathtub and said, Eureka. So, just know that if you ever have to physically measure volume for a shape that's not nice, just use displacement to help you out. Now, let's start with what is quite possibly the absolute easiest type of thing to calculate volume for: a rectangular prism. So, what we have here is this is a right rectangular prism. And we have, what do we have? We have the height is 2, the length is 5, the width is 3. And we're asked how many unit cubes, and these are in units, so 5 units, 3 units, 2 units. How many little unit cubes can we fit in here? Well, let's mark this off. This is in fifths, so 1, 2, 3, 4, 5. This is thirds, 1, 2, 3, and this is 2, so 1. Okay, so what I can do is I can break up this rectangular prism into little cubes, because I know that there's 5 units this way, 3 units this way, 2 units this way. So let me go ahead and try to sketch this. In fact, let me kind of put this back line in here. Actually, both of these back lines, just to help me. So there's that, and I also need that guy there. Okay, so let me break this up. So 1, 2, 3, 4, 5 that way, and then 1, 2, 3 that way. And of course, 2, and maybe I'll do this one in a different color just so it doesn't get too messy. I'll do this one in yellow. And then 2 this way. And in fact, let me break this up this way as well. And I'll break it up this way too. And what you can kind of see, and this isn't my best drawing, but what I'm trying to illustrate is that this is kind of like 2 layers of cubes, because the height is 2. The first layer has 5 times 3, which is 15 cubes. The second layer has also 5 times 3, which is 15 cubes. So really, we're just taking the area of the base and we're saying, well, we have, in this case, length times width, number of cubes. And then how many layers do we have? We have height, number of layers. So for this example, well, it's going to be 5 units times 3 units, that's the area of the base, times the height, which is 5 times 3 times 2 is 30, whatever our units are. And it is indeed a volume measurement, a 3-dimensional measurement, so it is cubed. So again, this isn't the best drawing. I'm not the best drawer, so hopefully this is kind of clear what's going on here. And this argument has nothing special about the numbers here, 2, 5, and 3. We didn't really care about them. We just cared they were the length, the width, and the height. So we can write volume as, I'm going to write it like this, length times width times the height. Or if you like, you can simplify this and say it's the area of the base times the height. So, we have a nice formula for the area of a rectangular prism. But luckily, and this is very, I shouldn't say lucky, but it's a very cool fact, that this basically works for any type of prism that you like. The fact that there's a rectangle down the bottom doesn't matter. And it all has to do with this principle called Cavalieri's principle, who was an Italian mathematician in the 1600s who came up with this. And what this principle states, I'm not going to prove it, but just note that there is a proof out there. It is proved that this is always true. If you have two three-dimensional objects, and they're such, the following holds. They're such that the two objects, G and H, have the same height, that the height is the same for both of them. And furthermore, if you cut them at a cross-section to make a cross-sectional area you can measure, if the cross-sectional areas are the same at every height that you cut them, then the volume of both of your objects is indeed the same. And if you look at this object here, well, this is some kind of lumpy and bumpy prism-like object, I guess. The top and the bottom, we'll call them the bases. They're not polygons, so we can't use any of that nice polygon machinery. But if I told you that, well, the bases have an area of 15 units squared, then let's think if this indeed satisfies Cavalieri's principle. Let me tell you that the height here is still 2. So, in this case, what do we have? Well, we have that the height of these objects is the same, and we have that the area of the bases are the same, 15 units squared, just like this guy. And the other thing is, the cross-sectional area, if you cut it at the same height in both places, also has to be the same. But this is a prism-like object, so if I go up here, some sort of height, let's say to here, let's call this distance x like we did here, and I take a cut here, and I do the same here. I go up to a distance of x, and I take a cut. Well, the cross-sectional area is going to be the same as the area of the base in both of these guys. So our cross-section, if we cut it, say here, here's our cut. Let me make this cut. There it is. And I take that over here. There's my little cross-section. Let's say that area is 15 because it's a 5 by 3 rectangle still. I just cut a rectangle out of this. And same here. If I cut this at height x, it's going to look, I'm going to just sketch this, but it's going to look something like that. And again, this is just a little sketch, so it might not be totally accurate, but it's going to look something like that. That cross-section, the exact same as the bases here. That's going to have an area of 15, no matter where I cut it, since it's a prism-like object. So, this satisfies Cavalieri's principle. So we know the volume of this is still going to be the area of the base times the height. And we're told that the area of the base is 15 units squared times the height, which is 2 units. Remember, height is a one-dimensional measurement, so just 1 unit. And 15 times 2 is 30. Units squared times units is units cubed. So this whole formula of area base times height is applicable to all prism-like objects, where the top and the bottom they're the same objects with the same area, and you just kind of draw a little right angle kind of sides between them here. So in general, and this is very nice, the formula for any prism-like object's volume is area of the base times the height. That's all there is to it. If you look up formulas for volume of various prism-like objects, you might see them differently, but it's all the same idea. In fact, you might see that, well, a cylinder is a prism-like object. There is a circle. There's the same circle just below it. You're thinking like a soup can or something. And if we have radius r here, you might see that the volume of a cylinder is pi r squared h, where we have this height h. But if we think about that formula, it is indeed just the area of the base times the height. The area of the base is pi r squared. So again, this is just the area of the base times the height. And that works for any prism-like object. So we have a little problem here. We know the following things. We know we have a cylinder. It has a height of 10 meters, and its volume is 125.6 meters cubed. Now, we want a square prism with a height of 15 meters, and we want it to have the same volume. So tell me the dimensions of that square. What is the side length of that square? So I think you should try this before you see me do it. My suggestion is sketch the cylinder and the square prism to kind of get a feel for what the problem is asking, and then see if you can solve this problem here. So pause the video now and try it yourself. Okay, let's go ahead and do this. So let me sketch both of these things. So there is our cylinder. It has height of 10. And we also have a square prism. So let me draw my square prism. All these sides are the same length. So there it is. And let me just make a little copy of this. See if I can do this. There it is. Move it up there. Join up the sides. So there is my square prism. Again, this is just a sketch. It doesn't have to be perfect. And to say that it is indeed a square in its base, I'm going to do little markings. So there is a nice right angle marking. And I'm going to say that all sides are the same length. Okay. So we know that the volume of our cylinder is the area of the base, which is a circle, times the height. And in fact, if you think about it, we don't really need the fact that the cylinder has height 10 meters. That's a little bit of a red herring. We're given the volume. So we're just given the volume, so let's just use it here. So we know that the volume of our, let's call it square prism, maybe pris for prism. Well, again, it's area of the base times the height. And we're told that the volume is 125.6 meters cubed. In fact, the fact that they tell us that it's the same volume as the cylinder doesn't really matter. They're giving us the volume of this prism. Well, maybe instead of giving us the volume, they could have given us the radius here, and then we'd have to calculate the volume. That could have been a possibility. But in this problem, they just give us the volume. Okay, so what is the base? The base is indeed a square. So we can just fill this in. This is s squared, side squared. So let me mark what s is. S is the side length here, times the height. And we're given the height. The height in this case is 15. And this equals 125.6. So let's divide both sides by 15. And we get that S squared, oh, wrong color here, S squared equals, say, 8.373, roughly, I guess. Maybe I'll put an approximate equal there. And we'll take the square root of both sides. And we're taking the square root of both sides. Remember, if S squared equals some number, then the square root could be positive or negative. But we're asked for a side length, so there's no way a side length can be negative, so we're just going to report the positive value. That's fine. So we get that S is roughly 2.894, let's say, meters. And remember, we're asked for a side length, which is a one-dimensional measurement, so our answer should be just meters to the power of 1. We just have this one dimension that we're measuring. Now we can start talking about pyramids. And again, just a reminder, we're only dealing with these right regular pyramids, where the base is indeed a regular polygon, so all sides and angles are congruent, and it's a right pyramid, which means that the center of the polygon is right above the tip of your pyramid. Okay. So it can be shown, and I will get you guys to most likely review this in a different place, but it can be shown for a square pyramid, and it's just with one particular height, that the volume is indeed the area of the base times the height over 3. And I'll just kind of sketch the idea of why this is the case. So here is a little explanation. I don't know how good this is going to be. I'm not very good at drawing a cube, but you guys just imagine that this is a cube. So what I'm going to do is I'm going to draw a diagonal line to the opposite corner for each of these 8 vertices. So if I do that, and this isn't in 3 dimensions, so it's kind of hard to draw it, but that's really what I'm doing. And it turns out that where those meet, this splits the cube into 6 pyramids. And from that idea, well, you can reason that the volume of the square pyramid is area of the base times the height over 3. And then, well, we can just use Cavalieri's principle to kind of help us determine the volume of any other pyramid. We have to use a little bit of similar triangle arguments if we want to show it precisely, but for our purposes, that's fine. We can just say we're using Cavalieri's principle. So we can say that the volume of any pyramid is area of the base times the height over 3. A lot of people mix up the formula for prisms and pyramids, but remember that with the same height and the same base, well, pyramids have prisms have 2 bases. So if you join these up to make a prism here, if it has the exact same height, if this is your height, then it's clear that the prism is larger than the pyramid in volume. It has more volume. So just remember that the pyramid volume formula is going to be smaller. And of course, dividing an expression by 3 makes it smaller. So it's like the prism divided by 3. And also, we're going to think of cones as pyramid-like enough, or I should say right regular pyramid-like enough for us to use this formula. So if we have this cone, so here's a circle, and I pick a point just above the center, and we call that length h, and then I make it into a cone. So let me in fact make the back dotted so it's a little bit easier to see. Just bear with me here. So there we go. Then we can use the idea of the pyramid formula here. It's just the area of the base times the height, but now divided by 3. So let's go ahead and do it. So maybe I'll write over here, volume is the area of the base times the height over 3, which is of course pi r squared times the height over 3. So this works for a cone as well.